go with Old Crow tephra. Yeah, like I said, a bit of a security blanket here to dive into the Quaternary. So I'd like to acknowledge the group of collaborators that worked with me on this project. So in the upper left there is Serhii Buriak, who just finished a PhD with Britta Jensen and I, and he's now an assistant professor at MacEwan University in Edmonton. And there's a group of Britta's graduate students who did a lot of the lab work in this project. And then finally, Mia Cook, who's now, I believe, a rotator at NSF in the paleo programs. And she provided really helpful sediment samples from one of the marine sediment cores that I'll talk about today. Okay, so let's get situated in Beringia, in the eastern part of Beringia, the kind of the vast quasi-contiguous unglaciated area of Yukon and Alaska and Siberia during the last glaciation and certainly previous glaciations as well. We've got the LGM glacial limit here for the Cordilleran and the Laurentide ice sheet, and then the ice over the Brooks Range, of course. And so the moral of this map of this kind of image, this iconic image, is one of expansive lack of glaciation, and that provides a real opportunity for Quaternary scientists who are interested in terrestrial records of environmental change, particularly at high latitudes, because as you know, glaciers are just excellent at erasing sedimentary history, and so our records of environmental phenomena and so on prior to the LGM is really scant. So Beringia is a great place to do that kind of work. And so, that glacial legacy or the legacy of those glaciers and ice sheets that didn't quite make it into the interior of eastern Beringia largely is due to the production of fine-grained sediments as a result of glacial erosion and the reworking of those sediments primarily by fluvial and aeolian activity. And so this is in the forefield or near the forefield of the Kaskawelsh Glacier, which is a large outlet glacier of the St. Elias ice fields and in the Yukon Territory. And you can see the the cloud of fine-grained sediment that's being carried by the Slims River from the Kaskawelsh Glacier and reworked by wind. And what happens in Beringia over successive glacials and interglacials is we get these spectacular these spectacular sedimentary records of both glacials and interglacials, in some cases going all the way back to the latest Pliocene. And so this is a site from central Alaska on the Yukon River called the Palisades. It's the most terrifying site I've ever worked on as a Quaternary geologist. That's about, I don't know, 70 meters, 70, 80 meters. So what for the US here, what's that, 200 feet or so of frozen near vertical glacial silts, but also interglacial forest beds. And so this provides that incredible opportunity to peer back at previous warm periods and also at the record of previous environments through glacials. This is a really neat region for all sorts of things. Permafrost first appeared here probably during the latest Pliocene. If you sort of squint and geofantasize a little bit, just to borrow a term from Brent Ward, you might be able to pick out this ice wedge cast here in some Pliocene gravels, indicating the presence of permafrost on this landscape, which subsequently thawed and filled the ice wedge that melted out. Permafrost in this field area, in parts of this field area, probably persisted through multiple warm interglacials of the late and the middle Pleistocene. These are about 700,000-year-old ice wedges. They're overlain by tephra that has really secure chronology that indicates that these ice wedges, and by extension the permafrost itself, hasn't thawed during interglacials like stage 11, stage 5, these warm sort of super interglacials in the Arctic. As a result of this permafrost legacy, we get treasures like, really incredible faunal records, both in terms of bones and DNA. This is a mummified baby mammoth that was exhumed from a placer gold mine in the Yukon Territory a couple summers ago on the right there. ground squirrel skull coming out of permafrost, and then a leg bone from a mammoth at a mine a few years ago. And the permafrost preservation of all this stuff is what makes it such a fascinating place to work. Because of that permafrost environment in these sediments, we have really incredible preservation of organic biomolecules too. So the ancient DNA community really likes this place as a place to work. So this is Scott Cocker at University of Alberta, drilling permafrost samples from mine, and then Louv Dahlen and Pete Heinzman and Britta Jensen at Chi-Chi's Bluff on the Old Crow River in Arctic Yukon. They're kind of frowning because the forest fire smoke was so bad last year. We got about 2 hours at this site and then had to go back because the smoke was so bad. But just remarkable preservation and lots of opportunities for multi-proxy paleoclimate, paleo-environmental reconstruction. The issue here is, as you know, it's really hard to tell time after radiocarbon. So all of the research on past climates and DNA, glacial history, et cetera, going through this is reliable. It is dependent on a good, reliable chronostratigraphic framework. Okay, and so the tephra is in this field area is what really allow us to exploit the long sedimentary records of glacial and non-glacial times in eastern Beringia. So we have probably hundreds of tephra in this field area in Yukon and Alaska. This is one of the prettiest. This is called Pal tephra. It's Middle Pleistocene. It's exposed really nicely at the Palisades. I kind of cheated here. This is a scanning electron micrograph of Old Crow tephra, which is the tephra that I'll focus on today. So the tephra are really beautiful close up. They are everywhere. These aren't the nasty kind of basaltic tephras that you find in Iceland that kind of blend into the dark sediments. These are typically pretty easy to see in the field. And once you get your eye keyed in on them, they start to become old friends, and you can pretty quickly start to pick up the framework in a given field area and figure out where you are in time as you're working these sites. So the region is basically fringed by volcanoes from a couple different ranges. The ones of interest in Yukon and Alaska are really the Aleutian Arc and Alaska Peninsula volcanoes. These are formed due to subduction of Pacific plate kind of along the Aleutian Trench. Moving further into mainland Alaska, we have the Wrangell volcanic field. So here's Sanford and Drum. These are really active volcanoes. I think that's the Alaska Highway there. And these volcanoes are associated with subduction of the Pacific plate kind of underneath the North America plate. So collectively, these many volcanoes are responsible for spewing out the hundreds of tephra that now find themselves in the sedimentary record of eastern Beringia. So we use these tephra in a couple different ways, right? We use them to correlate sediments between sites, and then we use them to directly date sedimentary sequences. So I'll just kind of talk briefly about how we do that. One example here, this is Old Crow tephra on the left. We're subsampling it just to get a sense of grain size variation through the eruption. So a particular tephra could be dated at multiple sites here across eastern Beringia, and that would give us, even if we don't know the date, right, that would give us a kind of a moment in time in those sedimentary sequences, as long as we can convince ourselves that the tephra are the same. So here's an example, right? In that prior one here, we're in the Fairbanks region, where Old Crow tephra is really thick, and we can go further into Yukon territory in subarctic Yukon. We find the same tephra, and we can identify that moment in time, and that's really useful. And then, we'll talk more about directly dating in a second. In terms of how we work with these tephra, we use multiple lines of evidence. The geochemistry is sort of the prime way that we fingerprint and identify and correlate tephra. But something that has really come out of the work on Old tephra that I'll discuss here is the importance of the sort of ancillary data that we get from being geologists, right? So the stratigraphic context of the tephra, the mineralogy, glass morphology, and chronology, and I'll add to that paleo-environmental context. These are all really important pieces of the puzzle in both fingerprinting tephra, but also correlating them across space. And no single one of these lines of evidence, whether it's age or just stratigraphy or just glass morphology or geochemistry, is really sufficient to unambiguously link these tephras across the subcontinental kind of region of Beringia. There are, as I said earlier, there are hundreds of these ashes, many of them coming from the same volcanoes, so same eruptions that are very tight geochemically in many cases, and so we have to be really careful and use all of the kind of tools at our disposal as broadly based geoscientists to make these tephra correlations. Okay, so in terms of dating tephra, and we're kind of getting closer to the crux of the story here. We have a bunch of different ways that we can do this, right? So we can indirectly date tephras, and that might involve things like radiocarbon, for example, dating organics that surround a tephra. We could use paleomagnetism. Here's an example from central Yukon, sorry, pardon me, central Alaska. This is near Fairbanks. And so we have this tephra here called the HP tephra. And this tephra happens to coincide really nicely stratigraphically with the Bruns-Matayama boundary. So everything below this red dashed line is magnetically reversed, and everything above that dashed line is magnetically normal, right? And so we have our paleomagnetic reversal here at about 780,000. And, even in the absence of a radiometric age for our particular tephra, this would give us a really nice kind of indirect clue on its age. And it turns out, this tephra has been dated now by Serhiy Buryak. The one that I showed you there is actually wrong. Serhiy has redated this using uranium lead dates on zircon and the tephra to about 680 or so thousand years, plus or minus 50. Okay, so this is kind of a great example of using an indirect age to provide a constraint on the dates for a tephra. This can be easy or hard to do, right? Here's an example of some charcoal that's associated with a reworked tephra, which presents all sorts of interpretive problems. Pardon me, low temporal resolution, not temporal resolution. And with radiocarbon, obviously, we're limited to the last 50 or so thousand years. So indirect dating can be tough. We can get lucky, but it can be tough. So what we've been trying to do as a community for the last 30 or 40 years, actually now, is to get direct dates on the tephra themselves. And the kind of the prime way of doing this is using kind of the systematics of decay of uranium. And really, we're counting daughter products of uranium decay, whether that daughter product is a physical manifestation of the decay of U-238 through to lead-206, which involves alpha decay and ejection of a helium nucleus, which actually causes a physical damage to the mineral or glass in this case with tephra. And with various lab treatments, we can actually see the manifestation of that physical damage. And so in this SEM image here, or this light micrograph, these are what fission tracks look like once you etch the glass with dilute hydrofluoric acid. And that allows the damaged portion of the glass to dissolve away. And so we can count and measure the density of the fission tracks on a glass shard, make a bunch of corrections, and really we're counting decay at that point. And so this allows us to get a direct age on the tephra itself. In other cases, we're zapping a primary magmatic mineral like zircon, So here in this lower image, we've got a light micrograph of a zircon grain. These two pits here, these are ablation pits from the laser ablation ICP-MS that we use to measure our isotope ratios. This is a really neat grain because if you kind of squint, you'll see these little rims around the grain. And so those are glass rims around that zircon grain. And so we know that the zircon was interacting directly with the melt at the time of the eruption that deposited that tephra. Okay, we'll talk about some of the limitations of fission tracks here in a second. All right, so let's turn to Old Crow tephra. This is gonna put all of these methods into focus. So Old Crow tephra, here it is in central Alaska. Our jet boat for scale. This is a big, tall, sort of 30, 40 meter exposure, and the tephra is just a monster. It is present kind of everywhere you look where you have sediments of late stage 6 to early stage MIS5 age. You find Old Crow tephra. And so all of these little dark splotches on the map are locales where Old Crow tephra has been discovered. This is an older map from Sherry Priest's big 2011 compilation about Old Crow tephra, with kind of the fantasy isopac maps of thickness of the tephra as you move away from what I'll call the presumed volcanic source for this eruption. So yeah, big point here. This tephra is present everywhere, and this becomes really important as we move forward into the analysis that I'll present here. So, from Togiak Bay, this is where Daryl Kaufman has done a bunch of work. Among others, the tephra is about 2 meters thick or so, in some kind of funky glacial sediments. Moving further inland by 500-600 kilometers, the tephra is still up to 20 or so centimeters thick. Most of that primary airfall, so just spectacularly thick. And then by the time we get, a couple thousand kilometers away from the presumed vent, the tephra is still present just about everywhere, and its thickness is in the centimeter range. So this is at Chiji's Bluff on the Porcupine River in Arctic Yukon. And this tephra is like I said, it's all over the place. Chiji's Bluff is about a 4 kilometer long exposure, and you can basically walk along at the level of Old Crow tephra and just follow it. It is just everywhere. Okay, so this tephra provides some really interesting constraints on all sorts of things, right? This is a paper from Brent Ward back in 2008 looking at deglacial gravels associated with the penultimate glaciation in Yukon territory and part of the Yukon that was glaciated. And Old Crow tephra overlies those gravels. And we'll talk about why that's kind of interesting and potentially problematic in a second, but provides a nice constraint on the age of those glacial sediments. In the realm of paleontology, this is Old Crow tephra at Chiji's Bluff in northern Yukon. This kind of smear of white across the exposure and coming over in this direction. And just off the photo is a bison metacarpal, and Old Crow tephra basically lies, it constrains the age of that bison bone. The tephra is a couple meters below, or a meter or so below, and then kind of sandwiching that bison bone is a presumed interglacial forest bed. And so, this was really neat evidence of one of the probably, among the first, it's the oldest bison to be found in North America. And the genetics of this coming out of this bone, indicate that it's certainly basal to all North American bison. So all North American bison descend from the bison represented, the group of bison represented by this particular specimen. So, the age of the tephra is really critical in making that argument. In terms of permafrost history, I don't know if there are any permafrost fans here. This is an image from a gold mine in the Yukon territory where we have Old Crow tephra. You can't see it in this photo. It's kind of thin and reworked, but you have to trust me that it's kind of present right at this stratigraphic level. And this is neat. It overlies these relict ice wedges. So these are ice wedges that still maintain their original morphology. And again, if permafrost had thawed during MIS5, then these wedges would not exist anymore, right? This is not the kind of massive ground ice that will form post-depositionally and or after thaw, deep thaw of the ground. And so this provides a nice datum on the persistence of permafrost through warm interglacials. Past environments, here is a kind of a compilation of some pollen, some paleoecology from sites across eastern Beringia, ranging from Emmerich Lake, which is a really classic Mar Lake record in the Seward Peninsula, and then some other sites kind of across Yukon and Alaska. And one of the things we see here is the presence of Old Crow tephra stratigraphically beneath paleoecological evidence for kind of full interglacial conditions. We have lots and lots of spruce and extralimital insect taxa and some extralimital plant taxa, indicating warmer than present conditions at a time, sometime after the deposition of Old Crow tephra. And just to belabor the point one more time, and to highlight the utility of the tephra in this part of the world, here's Old Crow tephra at Halfway House in the Fairbanks region. That's this section here. Here's Britta Jensen for scale. And so Old Crow tephra is right here. It's the thickest of the bunch. And she's pointing her trowel at the base of the last interglacial. And so we have a bunch of other tephra in this exposure, all of which are really pinned chronologically and in terms of the regional tephra framework by Old Crow tephra. Because Old Crow tephra is present everywhere, it is sort of the linchpin on which the framework for tephra studies in this field area rests. I mentioned something about the volcanic source of Old Crow tephra. I won't say much other than that. It was assumed for a while to be the Emmons Lake Volcanic Center. There's a lot of active work on this. Seth Burgess at the USGS has been critical of this. But yeah, lots of work going on here. So this is the sort of agnostic, non-partisan view of it. I'll just mention that this was the assumed source for a long time. This is a kind of a huge caldera on the order of 16, 20 meters or 16 to or so kilometer diameter caldera in the Aleutian Arc. For comparison, Crater Lake has a diameter somewhere on the order of 8 kilometers or so. So just a monstrous caldera forming eruption at some point from Emmons Lake. Whether that's the source of Old Crow tephra or not is still up for grabs. Okay, so let's get into the age, right? So this tephra is everywhere. Clearly, it is a useful stratigraphic marker. And then the question is, a stratigraphic marker for what? Okay, so Serhii Buriak put together these nice plots showing the evolution. I'm going to call it like the tortured, confused identity crisis history of this tephra over time, starting in 1978, when John Westgate and colleagues first started trying to do glass vision tract dating on these tephra. And so, what you can see is the age of this tephra has bounced around a lot, from basically late Pleistocene to 250 or so thousand years old. So let's talk about why that is. And this is kind of an important lesson when thinking about tephra chronology prior to radiocarbon. Okay, so this is not vision tract. This would be radiocarbon dating. And again, kind of getting at the point that, being really careful about finite radiocarbon ages close to their absolute limit. Okay, so, there's been this shaky consensus over the last few decades that the Old Crow tephra was deposited prior to the last interglacial during a period of cool climate. That is largely based on stratigraphy, in terms of its presence below organics and a forest bed that was assumed to be last interglacial, and then also the paleoecology of those sediments. So I've showed this figure before, right? Very little spruce at the time the tephra is deposited, some sedges, and then after a couple meters or so of sedimentation, we get a big peak in spruce pollen and other paleoecological indicators. We see this sedimentologically, stratigraphically. Here is a forest bed of assumed last interglacial age and old Crow tephra underlying. Again, forest kind of deposits with old Crow tephra underlying them elsewhere in eastern Beringia. And so that was kind of the happy story for a long time. And this was really largely supported by the glass fission track ages. So remember, the fission tracks are this sort of physical manifestation of radioactive decay. And the fission track ages sort of ranged and bounced around depending on, changes in methods and so on that I can talk about later in questions, kind of from about 125,000 to 150,000 with, plus or minus, 10 to 20% uncertainty. And the issue here is that glass can anneal or heal itself under ambient temperature and pressure conditions. And so the fission tracks have this really unfortunate, inconvenient habit of fading with time. And so we have to apply these different lab corrections to account for that. And there have been some changes in methods that have caused this age to bounce around. And just to be situated here, time is on our vertical axis, and the horizontal axis here is just the progression of the literature. Luminescence, similarly, the ages based on luminescence have bounced around quite a bit. So again, these aren't direct ages on the tephra itself, but are, minimum and maximum constraining ages on the tephra. There are a lot of assumptions and corrections involved in luminescence dating too, which I won't get into. I'm sure many of you here are more familiar with that than I am. There's a new age here by Lamoth et al. A few years ago, kind of coming in around 120 or 130,000 years old. But yeah, this age has bounced around somewhat too. Okay, so at this point, the story is sedimentologically, paleoecologically, and in terms of geochronologically, the story is still that Old Crow tephra is a stratigraphic marker for a cold period of time right before the onset of the last interglaciation, which is great. That fits with what we see in the field. And then a couple of years ago, Seth Burgess and colleagues at the USGS, they are really high-powered geochronologists doing really great work, very, very careful, lots and lots of dates. This is published in a 2019 paper in QSR and a 2021, I believe, paper in Quaternary Geochronology. I included that I'll put the links in the chat at the end here. And so they published these zircon, uranium lead, and uranium thorium dates of 200 or so thousand years ago. And so this is really highly disruptive and was kind of a cause for real concern for those of us who work in this field. And I'll kind of go through why in a second. Some issues here, when we're dating zircon in a tephra, we're dating the age of zircon crystallization, not the eruption age. So that's a potential complication. And there just is not a lot of lead, radiogenic lead, in a zircon of late Quaternary age, right? There just has not been a lot of time for uranium to decay to lead, and so there's just not a lot. There's a ton of common lead, and this becomes really complicated with some of the corrections that we have to make for zircon uranium-based ages of this sort of vintage. So yeah, this was a big problem, highly problematic, and let's kind of go through why. So here we have the Lizecki-Ramo benthic stack, time going from right to left, and here are the interglacials, right? Stage 7, 5, and the present, and then let's overlay. Okay, here are the glaciations, and let's put in kind of the two sort of competing hypotheses about the age of the tephra, the consensus age based on sort of those decades of fieldwork and fission track dating here marked right there. And then the disruptive new uranium-based ages for Old Crow tephra. And so as you can see, this presents a real problem with identifying what those interglacial sediments are that overlie Old Crow tephra. In some cases, Old Crow tephra is seemingly reworked into interglacial type sediments. And if that's the case, and these new zircon ages are correct, it implies that those interglacial sediments are actually stage 7, or it implies that all of stage 6 is represented by a meter or so of sedimentation. Anyway, the point is it throws the entire tephra framework into disarray for this field area. And so we were very troubled by this and decided we had to kind of come up with an independent way to think about those ages. And so we decided to turn to the marine sediment record. Here's the JR, God rest its soul. We're not using, oh no, the cores are from the JR actually, yeah. So we were inspired by Vera Ponomareva, who is a Russian tephra chronologist, and published a nice paper in 2018 based on some Holocene late cores in the Chukchi Sea. And what was really fascinating in Vera's paper is that there are shards of a tephra called the Aniakchak tephra. This is a mid-Holocene tephra that are present kind of throughout the late Holocene just as background marine sedimentation. So these are detrital grains of Aniakchak tephra that are making their way right now and throughout the late Holocene into the Chukchi Sea where they're deposited at that core site. And it's not just shards of Aniakchak tephra that were still being deposited in the Chukchi Sea, but also Old Crow tephra. So this map shows the distribution of Old Crow tephra sites in Yukon and Alaska. And Vera documented Old Crow tephra still being presumably eroded from land, making its way into the Bering Sea, out through the Bering Strait, and into the Chukchi Sea, where it is deposited in late Holocene marine mud as a detrital tephra, as detrital glass. So not a visible layer, but as just a background component of the detrital sedimentation. And so that made us think, holy smokes, if Old Crow tephra is still being reworked from the landscape, could we use that fact and just try to date its first appearance in the background marine sedimentation and get an independent age for that tephra using a nice kind of marine delta 018 kind of isotope curve. And so I'll just point out a couple sites here. So the sites that I'll mention today are U1345 and U1343. These were collected in the last 15 years or so. I'm going to also point out these core sites in the Gulf of Alaska. And one thing that's interesting here, we have looked exhaustively for a visible bed, a thick bed of Old Crow tephra at all of these sites, and it's just not there. So we have collected samples of every visible ash over the last 300,000 years, and spent a lot of time on the electron microprobe, and not a single one of them are Old Crow tephra. So that's kind of interesting. But nevertheless, we decided we're going to look at these two core sites. Yeah, these two core sites, and see if we could track when Old Crow tephra first appears as a non-visible detrital component. All right, so I'm going to take you first through U1345 because that's the data set that we published a few years ago. And yeah. All right, so from U1345, here is the isotope stratigraphy for that core. So nice, clear identification of the Holocene, stage 5 and stage 7. It's not the greatest stage model. You'll see that sort of late stage 6 and stage 5 transition is got pretty poor resolution, but I'll talk more about that in a second. And so these were the samples that we looked at, and we figured we would really be able to tell apart these two competing hypotheses. Here is the fission track age for Old Crow tephra, and these are the new uranium-based ages. So one of the problems was, we separated about 2,000 glass shards from the marine core sediments that Mia Cook provided us, and we needed a way to efficiently identify the shards of Old Crow tephra from the background or from a really heterogeneous mix of glasses that are being eroded from the landscape. And Matt Bolton, who's doing a PhD with Britta Jensen, wrote a really great bit of code to do some machine learning identification, basically to pick out Old Crow tephra versus not Old Crow tephra. And we're working with Matt right now to expand the utility of that tool. And we'll just mention that, Britta, who's sort of the tephra guru in this crew, went back and independently looked at all of these data, and we didn't have any sort of false positives or false negatives. So the machine learning algorithm worked well, but we confirmed everything with expert knowledge. Okay, so I'll work through sort of the results here from U1345. So what we'll do is we'll just work through in these time windows and figure out and have these very specific questions that hopefully the tephra data will allow us to answer. And so we first looked at a window that predates the supposed uranium-based ages for old tephra, and the thought was the tephra shouldn't be there, right? And here we have the old crow reference samples. We've analyzed this tephra thousands of times, and then the unknowns from the particular time window are going to be represented by the colored symbols. Okay, so old crow tephra is just not there, so that's great. That was our blank. Moving forward into the period of time that's covered by the uranium-based ages. Again, if the uranium-based ages were correct, then we figured old crow tephra should be here. This is a really widespread tephra in the landscape, and it should be reworked really, really quickly into the marine system. But it's just not there. We have one possible shard at 165, but otherwise nothing. Moving forward to if the kind of the classical conception of old crow tephra as a marker for late stage 6 and the onset of stage 5 was correct, then we analyzed a bunch of samples in this time window. And okay, yeah, here it is. There is a ton of old crow tephra. All right, so here are our unknowns for that time window, and a bunch of them, about half of them, in fact, overlap with the geochemistry of the reference sample of old crow tephra. I'm just showing one pair of oxides. You could make these same plots for any combination of oxides, and it would work. And then another interesting thing. Okay, well let's just keep going here. Actually, so the tephra first appears in the sediment record about 158 or 9,000 years ago. And then it really dominates that detrital shard population in terms of the percentage of shards that are old crow tephra for about 15,000 years. Okay, and so the implication of that would be the tephra is at the surface on the landscape. It's being actively reworked for that time period. And then we also looked at a bunch of samples for the 100 or so thousand years after the last interglaciation. Or after the supposed deposition of the tephra. And just like we would have suspected from the work in the Chukchi Sea, every one of the samples that spanned this age range had a little bit of old crow tephra. Okay, so if we look at that as the percentages of the analyzed shards that were old crow tephra, it's not a lot, right? So it's at pretty low concentration, but it's present in every sample. So this sort of confirms the story from the Chukchi Sea of active background reworking, erosion, and fluvial transport of that tephra into the marine sedimentation system. Okay, so I have a couple minutes left here. I want to leave lots of time for questions. So what about U1343? So, we put this paper out, and, there are some problematic implications of this, which I'll talk about in a second. But we really wanted to take another stab at this with a different marine sediment core, with a different age model, and kind of see where we were at. So here's the core that I just showed you, and I'll show you some preliminary data, really kind of hot off the microprobe in the last few weeks, honestly, from U1343. Just to think about the paleogeography here. Yeah, so here's the Yukon River. So thinking about where the Yukon River would have sort of mouthed out into the Bering Sea during sea level low stands is kind of an interesting question. Jeff Bond at the Yukon Geological Survey has published a map to kind of have some ideas about where that drainage system would have been, but still a bit of an open question. So this also kind of allows us to get at that uncertainty in terms of how old crow tephra is delivered to the Bering Sea during sea level low stands. Okay, so I've shown you the U1345 data up here just for context. So here's the benthic 4M delta 018, which is what our glacial and interglacial chronology is based on. And then here's U1343 down below. And a couple things jump out, right? So here these age scales are sort of the same, right? So a couple things jump out. One is we have a much better identification of the sort of the peak of stage 5E in U1343. There's much better resolution of that transition from the depths of stage 6, the glacial termination, and the isotopic sort of a excursion, I guess, or the isotopic low associated with the benthic forehand delta 18 with stage 5. So our chronology is maybe a little bit more reliable here, and that's just due to the poor sample resolution in U1345. So interestingly, okay, I guess the other thing I'll mention here is that we're doing the same analyses, right? We're just looking at fine grain sediments, but we decided to look at two different grain size fractions. For those of you interested in this kind of thing, I can talk more about it later. But 1345, we looked at the 75 to 150 micron fraction because that's what was available and already sieved. For U1343, we got the raw samples from the IODP repository and looked at both a finer fraction and a coarser fraction to see if there were any biases associated with grain size. And I haven't plotted the data, but what I can tell you is there is no bias. So if it's present in the coarse fraction, it is also present in the fine fraction and vice versa in terms of lack of presence. So interestingly, maybe a little bit problematically to some extent, we still need to figure out what's going on here. Old Crow tephra first shows up in U1343 at about 170,000 years ago. So, earlier than in U1345, still within barely our estimated age model uncertainty, but I mean, really barely. Okay. Still, no tephra prior to that point. We're analyzing samples from this interval right now just to confirm. And we still have that same pattern of, 10 or so thousand years of enhanced reworking and deposition of Old Crow tephra, where it comprises, 60, even 70% of the detrital shard population. And then that concentration tailing off through time and the tephra being present at relatively low concentration after that. Check the time. Okay. Okay, so there's a lot of active work going on that is relevant to this. I'll just mention there's a group at Brown that is working on Emmerich Lake and kind of coming up with their own independent age models based on I think rubidium strontium ratios. I think in terms of a kind of a erosion or weathering proxy. So lots of work going on in this. It's still kind of a highly contentious age. And so, yeah, we're really going to need to hone in on this and nail this age down if we're going to make progress on using records like the Emmerich Lake record. And certainly if we're going to have some confidence in all this multi-proxy work that people have been doing in Eastern Beringia. So one of the problems here, I'll just mention this for discussion. For those of you that are interested in the glacial stratigraphy in the area, there are two sites in Yukon territory where Old Crow tephra overlies glacial deposits that are presumed to have been of marine isotope stage 6 age. And so the evidence from the marine sediment cores is kind of problematic in terms of the timing of those glacial events. You'd think that the stage 6 glacial record in the Yukon would have those glacial sediments a little bit later in stage 6 during sort of the height of that glaciation. So this is a bit of a problem that we need to think about in terms of our chronology. We're going to spend a lot of time analyzing more samples from U1343, and we're going to have a good talk with the marine sediment people to kind of reconcile these age models and figure out if we can account for uncertainty in the timing of the first onset of Old Crow tephra. But having said all that, Old Crow tephra is still stage 6. It's not stage 7. It still underpins the tephra chronology framework in Eastern Beringia. but with some interesting wrinkles that we're still just at the early stages of starting to sort out. So I think I will stop there. It's 8:47 my time, and that leaves some time for questions and criticism and comments. And I'm hoping to get some ideas from the community here about how we can move forward with reconciling, especially some of these glacial stratigraphy data with this new and unwelcome uncertainty on the age of old core tephra. So I will stop there. Yep. I'll just leave that up if you are interested. We published a paper on this I guess 2 years ago now, 2023, from the U1345 record. You're welcome to go see that as an open access paper. And stay tuned for more on U1345. So I'll stop and take some questions if there are any.
Okay, thank you very much. That was very interesting. I've never been very familiar with the old crow tephra uncertainties. I just wonder while the Bergen group were getting their questions together, is there any paleo mag excursion information from the marine sediments, for example, or other records that might identify short-lived excursions that would help with the chronology?
Yeah, so this is something that's ongoing with Yang Song's group at Brown. They're looking at paleomag in the Emmerich Lake sediments themselves. So they've identified a number of excursions, and that is active work ongoing with Minnesota to try to identify them. In terms of the marine record, I don't know actually. I'm not quite sure if there's good paleomag that's been done in terms of say paleo intensity or inclination declination to identify the excursions in the marine record itself. Yeah.
Okay, thanks. All right, we'll turn it over to Bergen. Do you have any questions there in Bergen?
Can you hear me?
Yeah, go ahead.
I just have a question about your paper from 2022, where you came up with the age estimate of 159 plus minus 8,000 years. Would you say that that is now the most accepted age of the tephra?
Yeah, I mean that's the age that I kind of have to go with. So the age model for that core was published by Mia Cook in 2016. We did a little bit of modification to the age model by, you know what, if I can share my screen again. Yeah. I don't know if that's working. Yeah, okay. So we did a little bit of fiddling around with that age model using nitrogen isotopes to align the U1343 record, pardon me, the U1345 record to the U1343 record using nitrogen isotopes. There is some really prominent structure in the nitrogen isotope record that Mia used to kind of realign those records. And that took advantage of the better stage 6 to 5 transition data in the auction isotopes for U1343. So we fiddled with that and propagated some uncertainties and sort of came up with what we thought was a conservative uncertainty of 8,000 or 9,000 years. I think the published uncertainty says 4,000 years, and we thought maybe a little more conservative there. So yeah, that's kind of what I'm going with. Having said that, you know, the U1343 data, you know, that age model is ostensibly, you know, a little bit more reliable when it comes to the 6-5 transition. And so it's problematic, I guess, that what should be a moment in time in terms of the onset of tephra sedimentation is so dramatically different with these age models. So we're going to have to get in touch with the Marine Corps people to talk about this. There are similar problems with marine sediment core age models when it comes to Dawson tephra, which is a late Pleistocene tephra. It has a very, very good radiocarbon chronology from land, just based on, you know, vegetated surfaces that are directly overlain by the tephra. And the age in the marine sediments is really different from the age that we get from the radiocarbon dated terrestrial record. So I think there's some interesting opportunity for evaluating marine sediment chronologies as well, and thinking about their uncertainties using these kind of data. The thing that we haven't really done is think really coherently about, are there any biases associated with the location of fluvial outflows, say during periods of low stand, that might influence, that might bias the timing of delivery of detrital sediments to these two core sites. And the other thing that we're thinking about is working with these IODP sediments in the Gulf of Alaska, and trying to look for detrital old crow tephra there as well. So yeah, we're working on that, and I'm going right now with that 160 or so thousand year age, because that's what we've published. But I think that's going to move around a little bit. I am pretty confident that it's not 205,000 years old. It's not a stage 7 tephra. I'm pretty confident in that.
Thank you.
Sorry, that's a long answer to a really concise question.
Any other questions for Bergen? Sure.
I think we're good. Thank you.
Okay. Other questions? Julie, no doubt, has a question.
I do. Nice.
Hi, Julie.
Hi, that was really fantastic. Your point about the glacial sediments in the Yukon, in many places in Eastern Beringia, we see during the early onset of glaciation, the glaciers are a little more extensive sometimes in the early parts than in the later parts as the sea level drops. Do you think that may have anything to do with the positioning of the old crow tephra in the Yukon?
Yeah, I mean that would help.
Yeah.
Yeah, that would really help. The sites, okay, the site in the White River, which is a site Brent Ward and his student Derek Turner worked on, is a till site, but it would be pretty close to the limit. And the other site is more in the interior, and it's actually outside the glacial limit, but it's glacial fluvial sedimentation, so it's a terrace associated that can be traced back to a moraine. So that would help things, absolutely. We might need that help we might need to invoke something like that, but
Right.
It's not super satisfying that the age kind of seems to be creeping a little bit older. And part of my problem with that is that there really isn't a lot of loessl sedimentation between old crow tephra and what we assume is the last interglacial forest bed. Kind of maxes out at around a couple meters, right? Maybe 3 meters in some sites, but normally it's either a meter and a half below the interglacial, or often reworked into it. And that's because that last interglacial deposit, for those of you who aren't working in permafrost, is often a thaw in conformity. So it represents thaw in the landscape, and mass movements, which then are sort of incorporating underlying sediments in these sort of weird log-rich organic dimictons. So the stratigraphy is not layer cakey and super simple, but it is consistent with the stage 6H. Great point though, Julie.
Thanks.
Okay, thank you. Any other questions from the audience?
I think there was a question in the chat.
Yeah, I'm looking at that now.
Question.
So yeah,
there's
a question here says, what processes can contribute to the significant uncertainty in dating the old crow tephra within the terrestrial deposits? And can the effects of these processes be isolated and quantified? Okay, so the fission track uncertainty, we're kind of stuck with that. The corrections involve, trying to deal with the annealing of glass. So we're looking at different heating methods and also correcting for the diameter of the fission tracks. The age has bounced around because the age of the standard, the glass monitor that's used as a standard to calibrate the age, keeps bouncing around in turns. So every time the geochronologists come up with a new age for this moldavite tektite, it changes the age, the fission track age of the old crow tephra. So we're sort of beholden to them. And that's really the main thing. I will mention that on the side of the uranium lead dates in zircon, those ages can those ages can be moved to what you want, depending on how you decide to group and average your uranium lead dates, how you decide to correct for things like thorium disequilibrium, or how you decide to correct for common lead. And so it is possible to take the data set that Seth Burgess and his colleagues published and recalculate those exact same isotope data using slightly different methods. And you can easily yield a 160,000-year-old age for tephra. We decided not to publish that because it was just a little bit sort of needlessly confrontational, and it wasn't really the point of the paper. But certainly there are a lot of corrections to incorporate when doing zircon-based chronologies on young tephras from these timeframes. So in terms of isolating and quantifying all those into some sort of, maybe like a Bayesian framework to evaluate uncertainty, I'm sure that's something that can be done, and we're working to directly date different tephras that are within that framework around Old Crow tephra, and that will provide a kind of a new and independent quantification of uncertainty, but that's in process right now.
Okay, thank you. All right, any other questions?
Yeah, hi from Manchester. Thanks for a fantastic talk, Alberto.
Thank you.
I just wanted to ask, you showed us some of the major element concentrations for the tephra. Are people quite happy the major elements is good enough to pick apart those tephra compared to other things, and evolution of the chemistry in the mountain things for different parts of that eruption?
Yeah, that's a really great question. I didn't talk about the geochemistry of glass. Normally when we're dealing with identifying glasses using their geochemistry, we would want to confirm things with the trace element geochemistry, or potentially even geochemistry of some iron titanium oxides. In the case of Old Crow tephra, it's actually really bizarre. It stands very, very on its own in terms of its glass major element geochemistry. There's nothing really like it. So analyzing the hundreds of tephra, it is an island unto itself. And so I think the approach that we took wouldn't work, for example, with say Sheep Creek tephra or Aniakchak tephra, or some of those that are a little bit less iconoclastic in their geochemistry. But Old Crow tephra really does stand apart, and as a result, we felt comfortable with this approach.
Nice, thank you.
Okay, thank you. Any other questions? Okay, nothing heard. So thank you very much, Alberto. That was really cool. I guess the message is don't have too much data. Make it simple. Stick with the first number you came up with.
Well, yeah, maybe. Yeah, I think, for us, the message is the stratigraphy always matters, and it's useful to go to land and think about that context. Yeah, I think that's the moral of the story for me. Yeah. Hey,
Okay.
Thanks for your attention. I appreciate the invitation, and hope everyone has an okay and strange day here. Yeah.
All right. Thank you very much. Appreciate it.
Take care, all. Bye.
Bye-bye.